Okay, another Heathkit dissection and introduction and demonstration. Once again, I'm going to start out with Chuck Penson's excellent book on Heathkit test equipment products and flip to the digital multimeters chapter. And I've already done a video on Heathkit's earliest digital voltmeters, starting with the IM-2202, which I have but doesn't work, and then the IM-1202, which was their first really affordable one, entry level, and then the follow-up IM-1212, which is the same thing as the 1202 but in a horizontal form factor instead of a vertical form factor, and then the IM-1210, which is the same thing as the 1212 but in a plastic case, and changing the neon or the Nixie tubes for LED display. So that came out, that last model came out in 1976. And the subject of this video is the IM-2202. So the IM-2202 was introduced in 1975, and Heathkit made it for about 6 years. This was a fairly high-end multimeter. It was not auto-ranging. That was still pretty much of a rarity at the time, very expensive option. But basically, as the book says, it was Heathkit's third digital multimeter, designed for AC or portable operation with built-in NiCads or C batteries. The NiCads provided about 8 hours of runtime after 14 hours of charging. Alkaline batteries gives about 6 hours of use. Unlike the Nixie tube readouts used in all the other Heath products up to this time, the 1202 used 7-segment neon displays, gas discharge displays basically. They were really, I think, similar technology to the Nixie tubes, but instead of one element for each character shape, it used a 7-segment type display, but it had the same basic technology as a Nixie tube. So with the gas discharge display, as it says here, they're called neon displays, really the same thing. It had AC and DC volts, AC and DC milliamps up to 1.99 amps, and also the ability to read resistance. The power supply was either 120 or 240 volts AC, and it came with a built-in folding handle / kickstand and a pair of test leads. There is another meter which I also have in my collection, and I'm going to cover that later, is the IM-2212, which was very similar in many ways, just following a year or two behind the 2202. And this one was auto-ranging capability, and because of that, there isn't a range switch. The big knob on the 2202 is the range switch. Then you've got function selection buttons. On the 2212, the knob is the function selection button, and the ranging is automatic. So back to the 2202. So this meter was kind of a noteworthy item when it first came out, and here in Radio Electronics, November 1975, is this equipment report. It makes note of the fact that until right around this time, laboratory grade instruments that were digital voltmeters were very expensive, and that the reason this IM-2202 can be reasonably affordable is because of the MK6013, MOSTEC MK6013 integrated voltmeter chip that contains all of the instrument's logic circuitry. Without it, the 3.5 digit auto polarity indicating meter would be about twice as complicated and costly. And they mention the dual slope analog to digital converter. They mention the ranges. They mention that it updates the readings 5 times per second. And they talk about the Sperry gas discharge type displays. Excellent readability, 0.55 inches high. They mention that it's a bit of a pain to get them plugged into the sockets, because Heathkit, instead of using the proper sockets for them, used socket pins which were hard to get aligned. And they noticed that it sure would have been less expensive if Heathkit had just used LEDs on here, because the necessity of having a plus and minus 170 volt DC supply for the gas tubes required a lot of extra circuitry and parts. And they mention there's an internal DC to DC power supply, 4 NiCad batteries, and that they don't think it's a replacement for an FET analog meter but a complementary instrument. Anyway, so a favorable review. And I notice on the same issue they introduced the Paella Gnome synthesizer, something I built once just for a lark because I couldn't believe it would be very good, and it wasn't. It was basically just a noisemaker, not an instrument you were likely to actually be able to use for anything. And I think I gave that, yeah, I did give it to my brother to play with, and then he stuck it in the closet, and you know, many years ago I found it in the closet and retrieved it, and I still have it. So here's my example of the IM-2202. This was a eBay purchase. I'd been waiting for one for quite a while to show up. And this one's had a bit of a rough life, but it's basically in good cosmetic condition. As I'll talk about later, it's basically functional and calibratable, but these switches in particular have seen better days internally, and the selector switch here has some flaky positions that work sometimes and not other times, and it's really not practical to repair them. It's a hermetically sealed unit, and you can't spray contact lubricant into it, so I've exercised it a bunch and got it so at one point or another it'll work on every range, but for the demonstration we're going to have some issues probably with it may not work on every range, but at least I'll be able to demonstrate the basic functionality. It's not something I would want to use in a laboratory at this time because of its intermittencies, but at the time this was made, this was a pretty nice meter, and a lot of bang for the buck for the dollar considering the time it came out. So let's look at the front panel. 3 jacks, one for milliamps up to 1.99 amps, common jack, and a volt ohms jack. There's a pair of alternate action buttons, one for AC and one for either DC or ohms, since that's always DC. It's basically an AC-DC jack that alternates between the two. And then another pair of buttons for either volts and ohms or for milliamps. And these again are alternate action buttons. And then on the range switch, there's off, that's the power on-off button. There's both volts and milliamps in the same set of 4 positions. 1 volt or 1 milliamp, 10 volts, 10 milliamps, 100 volts, 100 milliamps, and 1000 volts or 1000 milliamps, or 1 amp. And then a low current and voltage position. On the volts, even though it says 1000 volt range, it's actually limited to 750 volts max when you're on AC, If you're on DC, I believe it can go all the way up to what the range switch indicates. There are 5 ranges for resistance, from 100 to 1K, 10K, 100K, and 1000K or 1 meg range. And there's also a battery test feature, which uses the meter in sort of a hybrid voltage checking mode. It simultaneously checks the battery and also checks all the display digits or display segments by basically running the counter used for doing the voltage measurements without blanking the digits during the counting portion. So you can see all the segments lighting up briefly, but being brighter and more solid looking on the actual numbers you're trying to read. So it's sort of a simultaneous display test and battery test feature. Alright, here's a look over of the meter. The front has 3 of the older style banana sockets, or banana jacks. All the current measurements use this one for the positive lead. Common is used for everything, and this red one is for the positive lead for both volts and ohms or resistance measurements. There's also a hole here which accesses the 0 trim potentiometer on the inside. The unit itself is on 3 circuit boards, packed in there pretty nicely. It's a remarkably shallow piece of equipment for test equipment of that era. Now this circuit board here, believe it's single-sided. It's a very thin epoxy fiberglass circuit board, so it's a little higher quality and with plated foils. All of the calibrations except for AC are on this board. There are trim pots here and here, and several more down here. There's another one down there and another one just around the corner in there. So the primary calibrations are all done up here. This is the board that has, I think, most of the interesting stuff on it. Okay, here's with the top board flipped up, and it is designed to be flipped up for best access. The main IC is this MOSTEC MK6013, I believe that is. And that's sort of an early integrated voltmeter chip. It doesn't have all the stuff on it that later integrated voltmeter chips had, such as the popular Intersil 7106 and 7107 chips, which are still widely used today for 3.5 digit voltmeters. This one had a lot of the functionality, but it didn't have all of it. This chip's almost unobtainium now, so if you have one of these that's blown, good luck trying to find a replacement. Anyway, I lied before. This is not a single-sided board, it's a double-sided board. And it's all connected up with a wiring harness to the rest of the meter, and a few shielded cables as well, which run back and forth. And now the lower board has a fusing section down there under a shield, and there's also all the switching for the front panel push button switches and the selector switch, and then all of the resistors for the range selection. And over in the corner of the board with the IC down there, that's an op-amp. That is the circuit for the AC precision rectifier, or the AC to DC converter. And that's why its trim pot is down there in the center of the picture. There's also the large diodes down here, which I think are for the power supply, but I haven't actually checked to see what those are yet. The display drivers are also in this area. All those transistors and resistors in that area are the high voltage switching circuits for the display. Now the third circuit board, you can see the back of it there. That's the one that has the actual digital display on it, but that's about all that's on that board. It also does have a couple of ancillary functions. There's a couple of the trim pots on it. They can be right there close to where all the switching is taking place. On the bottom rear is the set of 4 C-size NiCad batteries. Now these are not the ones that came in it. When I obtained this, the original ones had leaked, so I had to clean up that whole area, and I bought new rechargeable cells, again NiCad types, from the local Batteries Plus Bulbs store. Here's the fuse for the AC power. There's the rear end of the AC power cord socket. There's the power transformer. And here is just a little terminal board with capacitor and resistor on it associated with the incoming power. And these 2 trim capacitors down here are part of the input attenuator circuit. Here's the rear of the unit. The only thing that's on it is the socket for the power cord. Now it's this funky type of power cord that I don't know how widespread it was at the time, but it's not the only Heathkit meter of this time period that had that kind of plug. I have not been able to find anything that plugs into there, so unfortunately, in order to power this up, I have to use alligator clips from another line cord. If there was more room in here, I could modify this and put in an IEC type socket. However, it would impinge upon the power transformer down there. I'm not sure it would fit. Might be possible, but I also don't want to modify this. And since I don't have it to use, just to demonstrate and have in my collection, I can use the alligator clip method. I'm thinking about possibly designing a 3D printed plug that'll work for that. That may be a future project. So let's turn this guy on. Got a nice 0 there, and a minus sign that's alternating plus and minus as it should if it's properly calibrated. It's right on 0, neither above or below, so it alternates. Let's do some DC voltage checks first. Okay, this is with the power supply set to 0 volts. Going to take it up to 1 volt. And it's sitting there at about 1 volt. I can go to the 1 volt range to get a little more accuracy on it. 0.994 thereabouts. Take it back to the 10 volt range. Now this does have a slow settling time, slower than we might be accustomed to with modern meters, but the manual does say that's normal. So right now we're showing 1 volt. Let's go up to 5 volts. And again, we're just about there. We can go up to 17, 18 volts. Pretty good. 32 volts. We've overranged the 10 volt range, and the meter flashes the most significant one to indicate an overrange. So I have to select the 100 volt range, and we're showing 31.9 volts for a 32 volt, and it just flicked at 32 there, so it's right on the edge. So that's pretty good. Down to 24 volts. Good. Okay, so I've moved the test leads so that the red is on the milliamp or current jack, and I've switched to the milliamp switch here. I've still left it on DC because I'm going to be giving it DC milliamps. I'm in the 10 milliamp range. which means it can actually go up to 19.99, but they label it as a 10 volt range. Okay, I've got power supply set to 24 volts. I've got a little milliamp, 40 milliamp tester here, which will allow me to control the current for the purposes of demonstration. I'm going to turn on my power supply. I get the indicator there that the loop is good, and with the knob in the middle I should be getting about 12 milliamps, which I am, 11.96. Now if I throw this switch here, it should take me to 4 milliamps, and it's just about right on the money. Move the switch back, it should go about to 12 milliamps. Throw the other switch, it should go up to about 20 milliamps, just a little bit shy. Throw the switch, should go back to 12 milliamps. Turn the knob, and I can go anywhere between 4 milliamps and go up to about 20 milliamps. And back to about 12. So the milliamp function works. Okay, I've got the meter set up, common and volts ohms on the plug, ohms and ohms here. I've got it set to the lowest range, 100 ohm range. I've got it hooked up to my Heathkit decade resistance box, and it's set to 0, and we're reading nearly 0 here. If I go up to 5 ohms, it's reading about 5 ohms. If I kick in 20 up here, it's reading 25 ohms. If I kick up to 2K here, it's going to overrange, so I have to select 1K here. It should be reading about 225, and it is, so that's good. Let's turn this guy back to 0 and take it up to 4K, 422. It's overrange, so I take it up to the 10K range. Let it settle in. 422, right on the money. Let's go up to the 100K range and give it something it can work with. Let's give it 500K. It's overranged. That's too much for the 100K range, which only goes to 190K, so I have to go up to the 1000K range. And we're reading just under 500K here, so that's really good. If I kick in an extra 30K, 500, you know, pretty close to 530K showing. So the ohms function is working really well, good accuracy. Okay, let's test an AC function. I've got it set to AC volts, and I'm in the voltage part of the range, and on the 100, which will take me up to 199 volts, so that's a good one to be in. My test leads are connected to the output of my Variac, so I'm going to kick this guy on, make sure it's turned all the way down. Turn it on, and I'm reading 0 here. Let's crank it up so it says we're doing about 40 volts. I have had some issues with this, with the meter on this range, that the switches are a little bit intermittent. Sometimes it'll read almost an order of magnitude lower. It should be working at 40 volts, and if I fiddle with the switch, I can usually get it to kick up to where it should be. But it's very iffy. Definitely getting an overrange there. If I'm up here in the 1000 volt range, I'm giving it about 120 volts now, and it's reading more correctly. So in that sense, it's working in the 1000 volt range, but there's a intermittency with the switches somewhere in this range. So I haven't been able to fix that. The switches are sealed, so sometimes it works, sometimes it doesn't. I'm just unlucky now. When I was calibrating it, I got it to work. Let's try taking it down to about 20 volts on the 10 volt range, which is the 100 or the 19.9 range. So here it's working. So the AC to DC converter is working just fine. I can get an appropriate reading on the 1000 volt range and on the 10 volt range. It's just that contact, I think it's not making a good contact on that position of the switch. Taking it down to around 10 volts, a little bit lower, yeah. So once again, it's working, it's just got a little bit flakiness in that position of the switch. And there's also a battery test mode on here. Where it's supposed to read around 6 volts. And that's what it's doing, 5 1/4 volts. And part of the way the battery test circuit works is that it's sort of pulsed, so that's why it's kind of jerky like that. So that's normal. It's reading that the batteries have a charge on them, and then I'll turn it off. So as far as working condition goes, I know the AC volts range works, but it doesn't work very well or reliably when the switch is in the 100 volt range. Otherwise it works. So I interrupted myself there, but it does work on lower AC volts. We've already checked it on higher AC volts. It works well in everything except this one part of the range. I haven't checked it on AC milliamps, but that should work because it's the same exact circuit except it goes through the AC to DC converter, which I know works. So it's just I would have to rig something up in order to be able to generate that. The meter just slides into the case. There's actually a big sheet of fish paper glued to the inside of the case here so that none of this stuff shorts out to the case. And here's the reassembled meter with its carrying handle / kickstand. If I undo the knurled nuts on each side, then the handle can be rotated up to the carrying position. Okay, here's the glory shot. Those are some beautiful displays. Nice and clear. They look more elegant than 7-segment LED displays. The segments actually join each other practically. It's too bad that technology seems to have gone away. Not that great of a kickstand, really. This unit was getting calibrations at some point, whoever owned it. I interpret that as being December 18th, 1980. And I don't know if that's a 5 or a 6. May or June 23rd, 1983. Apparently not since then. And I put my own little tag on there. Tested and calibrated Date, new batteries, all okay except AC volt works. Intermittent on 100 volt range and a little twitchy on the lower AC volts. It's all due to bad switch contacts. AC milliamps not really tested. So in the future I'll remember what went on with this. Okay, there's a great big schematic for this meter, and I'm going to go through it in some detail as I usually do with these videos, but some parts of it are so convoluted it's hard to follow, so I actually broke them out into separate sections for each sub-circuit, and where appropriate I'll use my sketches instead of the actual schematic. And some other areas I'll actually follow this schematic directly. Starting with the AC input, it's either 120 volts or 240 volts, and by using a jumper in a couple of different ways you can connect the two primary windings for those two voltages, and there's a couple different values for the power fuse depending on which voltage you're using. And curiously, you'd expect to see a big diode bridge sitting out here on the secondary, and the first thing we have is a diode going to the batteries and some other stuff, and then it's like, what's going on here? So at this point I'm going to jump to the sketch I made. Okay, here's the same thing. I haven't really simplified it, I just cleaned out the clutter. So the one side of the secondary winding is connected to circuit ground, and there's two grounds in here, the low noise ground and the regular ground, but for the purposes of my sketch and discussion they're just one ground. It's electrically common, it's just the way the foils are routed on the circuit boards and so on. Anyway, so there's a current limiting resistor, actually it's more of a charging current resistor for the batteries. And I don't know offhand what the voltage is here, but it's probably, you know, not a lot. A small number of volts, because it can't be too high or it would damage the batteries. The 4 NiCad cells add up to a nominal 5.2 volts. And there's a single diode again, the half-wave rectifier, and the resistor are all it is taking to charge it. And unless you unplug the meter, the batteries are always charging. There's no charging disabled during power off of the meter if you do it with the power switch. Then there is a half-wave rectifier going the other direction with a voltage divider on the output using a potentiometer, and that provides an AC reference test point for use during calibration if you're trying to use the meter's own voltage references. Then switch 5, which is the big knob on the front, it has lots of gangs to it. The first thing we do is use this as a power switch, so in all positions except for off, the two halves are connected together, so the point at the top of the batteries, whether it's power coming from the batteries or from here, half-wave rectified, ends up coming down here, and it goes to all the power supply circuits. If the meter is selected to battery test mode, then the bottom connection on the second gang of switch 5 is also closed, so you connect through here. I think I'm going to switch to using my pencil as a pointer. So connecting through here, and then this is the gang of the switch that's used for selecting the voltage range, and this is a tap off of it. There are other taps, but in this view I'm only showing this one, so it just couples this voltage here up, and then it goes to the voltage range input attenuator resistor voltage divider. At that point it's viewed like any other DC voltage that the meter might measure, and the meter's integrator is in its high sensitivity mode when selected battery test range. That's going to be discussed elsewhere. So the rest of the circuit operates just the same as if it were in the 10 volt DC mode, which is, or the 10 volt DC range, which is appropriate for something that's a little over 5 volts. So really that's all there is to the battery test circuit and the battery charging circuit. Except a little note I wrote to myself. There's some other contacts on switch 5 that have additional effects not directly related to the battery test measurement itself, but add some fine touches to it. One thing it does is it forces the display to read the minus indication all the time. I'm not sure why they do that. Maybe it's just another way to suggest that the meter is not in normal mode. And also the integrated voltmeter chip, IC-201, that's that MOSTEC part, between it and some of the support circuitry, it can be told or forced into a mode where it disables its internal counter latch functionality. So the way these chips all work is they have an internal counter and a comparator, and there's a slope that gets, or a voltage that charges up on a linear slope, and you wait till the voltage charges up to equal the input voltage that you're measuring. At that point it'll stop the counter, and whatever has counted up is a numerical value equal to the voltage or whatever you're reading, and then that gets latched and then displayed, and then the whole cycle starts over again with a new slope and so on. So the IC is told to disable its latch when you're in battery test mode, and that has the result that instead of having the display frozen and updating only every or 5 times a second, it actually lets the display show whatever's in the counter constantly. So it's just racing up from 0 to some count. Let's say the voltage is 5.2 volts on the battery. You know, it'll be 520 or something, and it's going to count up to that number 520 from 0, you know, and do that 5 times a second. And by disabling the latch function and letting the display constantly show the counter accumulator value, it looks like all the segments are on, but it's happening so fast that they're kind of dim. But then when the chip actually gets to the point where it's completed its count and actually wants to display something, then it's allowed to without all the flicker. So the end result is you get a minus sign that's forced on. All of the segments seem to be on sort of dimly, but the actual number of the battery test value is bolder, and you can actually read it, you know, 5.20 or whatever. So that's another function. That is deliberate. They didn't have to do that. They could have just left the meter to read the battery voltage and it would have looked normal. But the Heathkit manual points out that by doing that, the operator isn't going to get confused about whether he's taking a normal reading using the test leads on the front of the meter or if he's reading the battery voltage. By having a funky looking display during that mode, it serves 2 purposes. One is it reminds you you're not in a normal mode, and secondly, it provides a segment test for the display and for the driver circuits of the display. It doesn't really do that for the top digit, but by doing it for these digits, you know that all the segment drivers are working, and that's a big part of all of this circuit and what's inside the IC here. Now this part of the circuit is the AC to DC converter, which sounds like a power supply, doesn't it? I don't like to call it that. It's really a precision rectifier circuit, and so for the rest of this discussion, I'm going to call it by that name. I've kind of redrawn it here with some things drawn a little differently to make it hopefully a little easier to figure out. So here's the input signal from the function and range switches, and it goes to one gang of the DC, Ohms, and AC switch. This circuit only applies when you're in AC volts or AC milliamps. It does not apply in any of the DC ranges or the resistance ohms mode. So this switch here only couples the input of this circuit to the incoming input signal if you're in AC mode. And then the output of the circuit way down here can only escape and get to the rest of the meter circuit if that same switch is in the AC mode. If the switch is in the DC ohms mode at both positions, then this circuit is isolated electrically from the rest of the meter circuit. Okay, let's say we have an incoming voltage here. The first thing we do is we have a clamping circuit to protect the rest of the circuit. It's a pair of diodes going to plus 12 volts and minus 12 volts power supply with a current limiting resistor. So if the voltage here exceeds plus or minus 12 volts, it'll be clamped to those voltages instead of exceeding them, which could cause some component damage here. So it's a safety circuit. This FET and this bipolar transistor work in tandem to provide a low output impedance driver for the rest of the circuit. And this is pretty common, not for the most basic precision rectifiers, but for, I think, every one I've ever seen on commercial products. So having that impedance isolation function apparently helps the rest of it be more stable or a little bit more accurate. Now, I want to digress. So here's the schematic of a basic op-amp negative amplifier or inverting amplifier. You have an input voltage, it's applied to the negative input through a resistor Rin, and then there is a resistor from the negative input to the output called RF or R feedback. The output's here, and then the positive input's usually just tied to ground or something functionally equivalent. The signal's inverted, so if it's a positive voltage it becomes a negative one here, and vice versa. And the gain is simply this resistor value over this one. So if these are both the same value, then it's the same thing over the same thing, which is 1, so the gain is 1. If you put 2 volts on the input, you'll have 2 volts on the output, except it'll be negative 2 volts. And if this resistor is 10 times what this is, then the ratio is upside down, so you'll have a gain of 0.1. And if this resistor is bigger than this one, did I say that right? If this one's bigger than this one, then you'll have a positive gain, or a gain rather than an attenuation, essentially, so that the output voltage is greater than the input voltage. If this one's bigger than this one, then it's like an attenuation, and the output will be less than the input. So that's the basic configuration, and this precision rectifier is just a gloriously modified version of that. So here's the op-amp in the actual circuit, just like the one I showed, the positive inputs tied to ground. There is this low impedance or low output impedance driver, which just passes the input voltage through but makes it have a lower impedance. And then there's what's essentially a 10K resistor. It's a 9.95K. It's a precision resistor, and those often don't end up coming in exactly the values you want, so that's as close as they could come to the desired 10K. And then there's a 90K here, so the 10K and the 90K is 100K. And there is this gang of the switch 5, the big knob on the front, which only in certain positions shorts out this resistor, so it changes the input resistance, the Rin value, from between 100K to 10K, depending on whether this switch is shorting out the 90K part or not. And even though it closes some positions down here, they're not relevant, because these are only in the resistance range or the battery test range, which is not applicable to the AC to DC conversion or the precision rectifier. So it's really only the 10 volt range and the 100 milliamp range that this switch shorts it out. Everything else, it's got a, let's see, so this is shorted out in those two ranges, which turns it into a 10K input and a 10K feedback, so the gain is 1-to-1 then. Yeah, normally this has a gain of 0.1, but when you short out the resistor in those two ranges, then it becomes a gain of 1. Then there's a series capacitor, which just removes any DC component. It should only be having AC volts, and that's useful if your AC voltage is floating on a DC offset or bias. This would remove that DC component and leave you only the AC part. And this is just a loading resistor to ground. It helps this work better. So now let's get into the actual op amp itself. Some of these older op amps, this is I think an LM-301, fairly early op amp. It has a compensation capacitor that's required, and it can be connected in several different ways. In this circuit, it's connected from the compensation pin to the negative input, but it could be connected from pin 1 to pin 8. That's another way of doing it. But it's there for compensation, so this behaves the best in the environment, the range of types of inputs you're going to be putting through it. This is just a filter. There's the positive 5-volt power supply through a 15 ohm resistor, small filter capacitor ground that provides the positive power supply. You might think the negative power supply would also be 5 volts, just a negative 5 volts, but it's actually negative 8.25 volts. There's a resistor voltage divider from the negative 12 volt power supply to ground with these two resistor values and a small capacitor to ground in the middle that provides a negative 8.2 volt. Well, the op amp doesn't care as long as the voltages are greater than the voltage range of the signal you're going to be putting through it. And I happen to know that this meter doesn't usually have more than 2 volts of signal plus or minus from ground, so plus 5 is more than enough, minus 8.25 is more than enough. Their dissimilarity or their disparity is not going to change the signal at all unless you get high enough to run into one or the other of them. If you did, it would clip at 5 volts on the positive side or clip at minus 8.2 volts on the negative side, but that's not an issue here. The output is fed through a capacitor. Once again, I think it's there primarily to get rid of any DC component that might have gotten through somehow. And then basically what we have is our feedback. Now you can ignore this. This is a compensation capacitor. This is another compensation capacitor. What we really have is this feedback resistor, which is a 10K resistor. And that's the RF value from what I showed in the simplified version. And then you've got these two smaller resistors, one of which is active at any given time through these two diodes. So if the output swings positive, it reverse biases this and nothing goes this way, and it forward biases this diode, so the signal goes this way through this smaller resistor to this point Z. This is effectively the output of the op amp as far as this greater circuit is concerned. And on the positive swing it goes this way, on the negative swing it uses this path, but they all come back to this point Z. Now that signal is dropped to ground over a very low resistance circuit of a 301 ohm resistor and a 500 ohm calibration resistor. So you're basically providing the output voltage that's built up across this resistor, and this is effectively the output of the op amp. And then that voltage is fed back through the 10K feedback resistor to the input here, and so the gain will be either a gain of 1 or a gain of 0.1 depending upon whether this resistor here is shorted out. So what's all this junk about? Well, these are DC voltages here. It's not an AC voltage anymore. This rectifier diode provides only positive voltages here, and this one provides only negative voltages here, and then they're fed back and provide the gain and the stability of the circuit. But here's the thing. If you try rectifying the signal with just the diode, you won't get any signal through it until you get to the diode's forward voltage, which is typically 0.6 volts, maybe 0.7 volts. So if you had a signal that was only 0.3 volts, it would never get through, and there would be no signal at all coming out of this rectifier circuit. Well, that's no good. You wouldn't get any good readings if you did that. So when you put a diode like this in series with the feedback path, the way the feedback functionality, the negative feedback works, is it cancels out the voltage drop essentially as if it wasn't there, but it's still being rectified. So and then by skewing this voltage through these resistors to ground through this resistor, that's how you calibrate it. You can adjust the point Z voltage up and down a little bit to compensate for component value differences. So basically what we have here is a circuit that is generating an output that's boosted to compensate for the drop of the diodes. And then you're tapping off the positive only side, which, as I'll sketch in here, looks like that. There is no negative component to it because we're only looking at the side that you get voltage there when this diode is forward biased on a positive signal. You could just tap off the negative one too. It wouldn't really matter as long as the circuit downstream is looking for the right thing. And the downstream circuitry here is looking for a positive voltage. Anyway, so then there's a averaging circuit here, a resistor and a capacitor. It averages the voltage here. So the average is going to be perhaps right around there. So that's the average voltage you're going to build up at this point in the circuit. Then here's a filter circuit. It really has the same values. It's basically filtering any remaining ripple or whatever that you might get from the averaging circuit, so you have a nice smooth voltage out here, and that voltage is proportional to the average AC voltage. And then it's dropped across this resistor. And then this is an impedance matching resistor going to the rest of the circuit. It goes back through the other half of switch 2, and it continues on to the input of the integrator. So that's how we're converting an AC input signal, whether it's AC volts or AC milliamps, to a DC voltage that's proportional and can be used for the DC reading voltmeter circuit that follows this. Okay, here's the AC volts and DC volts measurement circuit. I've only shown the pertinent parts of the circuit from this much more complicated version. Although everything I show in here is correct, I'm not cheating anywhere. I'm just leaving out all the fluby dust that's not applicable to voltage measurements. So the black test lead is connected to the common terminal, which goes to circuit ground. The red test lead is going into the volts ohms jack, which is red, and there's a fuse here to protect the rest of the circuit. Here's the DC ohms and AC switch. Once again, it's a different gang of the same one that we've already looked at. It has a series capacitor, so if you're in DC measuring range, it shorts out the capacitor. You don't want it there. The DC won't go through the capacitor. It has to go around the capacitor. But if you're in AC mode, then the switch contact is over here, and the signal must go through the capacitor. And what that does is it removes, again, the DC component of whatever you're measuring and lets only the AC part pass. And then it makes its routing through some other switches. There's another switch that has a volt ohm position not a DC ohm position, but a volt ohm position and a milliamp position. It goes through there. It goes to another gang of the same switch. And you may note here that this says switch 3 and this says switch 4. The meter has these alternate action push buttons. So even though they appear physically to be two different push buttons, it's really one switch because the two switches are ganged together. And so switch 3 might be the left-hand button and switch 4 might be the right-hand button. But anyway, when you're in the volts ohms position or not in the milliamp position, the signal sails all the way through here and is applied to this switch 5 gang here. In the off position, the signal goes nowhere. In the 1000 volt, 100 volt, and 10 volt range, it's applied to the top of this big voltage divider, which goes to ground. These two resistors together add up to 9.9 mega ohms, in series with a 90K, in series with a 10K, and that adds up as a big voltage divider, and you'll tap off of, let's say we're in the 1000 volt range. Here's another gang of the same switch, and here's another gang in between. We have 3 gangs of the same switch involved with this measurement. So let's say we were measuring the 1000 volt range. We drop a bunch of voltage across these resistors, but we tap off through this resistor down here at the bottom. So the majority of that 1000 volts is dropped across these high value resistors, and then you have a small voltage across the 10K resistor. So what it's basically doing is just dividing the input signal down by 1 or more orders of magnitude. And a signal that would be 1000 volts here, if the switch is in the 1000 volt position, would only be 1 volt by the time it gets down to here. And again, this meter is really designed internally to work within a range of plus or minus 1 volt, but in reality it can go up to 1.99 or negative 1.99. But a 1000 volt input would give you 1 volt here. And then it's passing through the switch. It comes out the common of the switch. It goes through a couple more of the push button switches. It's routed straight through. And then it goes on to the input signal to the integrator circuit, which I'll get to later. So that's the path for 1000 volts. If we were in 100, we'd go through here, same deal, applied to the voltage divider, but now we'd be tapping off here, a little higher up in the voltage divider. So now a 100 volt signal would give us 1 volt here. And it's the same thing for everything downstream. And the same thing goes on. The 10 volt range, same deal, but look at this. In the 10 volt range, it's the same selector down here as for the 100 volt range. How does that work? It's using the same point in the voltage dropping, or the voltage divider here, as it does for the 100 volt range. Well, there's this additional gang of the switch here which shorts out a resistor in the integrator circuit, changing its gain, much like we changed the gain in the precision rectifier circuit by shorting out a resistor in certain ranges. The same thing happens to the integrator circuit. So it has a mode where it's looking for a 100 millivolt signal full scale or a 1 volt signal full scale. And so we're down to the 10 volt range now, and we're worried because it's the same resistor that got 1 volt at 100 volts. Now you're in the 10 volt range. 10 volts going to give you a tenth of a volt, but guess what? This switch over here in the 10 volt range shorts out this resistor, changes this integrator into one that's expecting to see only 0.1 volts instead of 1 volts. So it still works out the same. And that same game is played here. In the 1 volt or 100 millivolt range, it's the same contact. And assuming, again, you're in the voltage measuring range, this switch will be closed, and it bypasses the resistor divider altogether here, and it conditions it with these resistors here instead of these resistors, because now we're dealing with 1 volt or 100 millivolt, which are the voltages that the integrator is expecting to see already. So they're already in the right range. They don't need the help of this resistor divider. All we're really doing is switching them through these switches and then down to either the 1 or 100 millivolt range here, and then on out and on to the integrators like we looked at before. So the only thing I should say before is I looked at the battery voltage testing circuit before, and I said that it's injected into the top of the voltage measuring voltage divider. And here's that same switch redrawn. Here's from the plus terminal of the battery. It goes for these contacts, and it's injected up here at the top of this divider, and it treats it as if it's in the 10 volt range, and then it's conditioned without this actually being part of it, because in the 10 volt range you're going through one of these switches, or I'm sorry, yeah, in the 10 volt range, yeah, you're tapping off of here. So that's fairly straightforward. The only confusing part about it is how this divider doesn't seem to do enough of a job, because it's easy to forget about how this circuit over here is shifting gears of the integrator to expect a different voltage for full scale sometimes. So let's get down to the integrator here. All of these voltmeter circuits, digital voltmeter circuits, rely on, like I said earlier, charging up a capacitor through a constant current source in order to get a linear ramp voltage, and that's proportional to time, and a counter runs during the whole time the ramp is accumulating voltage until that voltage reaches the voltage of the input signal being applied to the integrator. At that point, the output of the integrator flips, and it tells the downstream circuit, in other words the voltmeter chip, that the count that it has in its counter is now proportional to the input signal, and it should stop counting and display the value. That's essentially what's happening. And like I said before, the sensitivity of this integrator can be changed depending on whether we're in one range or another. And one more thing, in the previously mentioned precision rectifier circuit, I pointed out there were these two switches that took the precision rectifier in and out of the circuit, depending if you're in DC or AC volts. These are the same switches, just redrawn here. So this out here is that precision rectifier circuit. You go out through it, you come back, and continue on to the integrator. So that is how voltage is measured. Alright, so here's the part of the circuit that measures milliamps, or current. The positive jack becomes the milliamp jack instead of the volts ohms jack, and there's a separate fuse. It's a 3 amp fuse. It's conditioned through these two gangs of the same switch, which is the volt ohms on one side of the milliamp, and they're in parallel, probably to handle the additional current, is my guess, or maybe just for convenience on the circuit board. Anyway, the current only passes through the switch when it's in the milliamps position. Then the other switch, the same gang of the complementary switch, it goes through that one in series, so it actually passes through that switch sort of 3 times. And then it's clamped in case the voltage potential on there is outside of bounds. If it goes too far positive, then it's clamped to the plus 12 volt power supply. If it goes too far negative, it's clamped to the minus 12 volt power supply, much like the diode clamps did at the input to the precision rectifier. There's these extra diodes here which perform additional clamping functionality. Then it goes to another gang of switch 5, which is the big rotary switch, and it's using the same 5 positions that are used for voltages, but in this case, instead of 1,000 volts, it's 1,000 milliamps, 100 milliamps, 10 milliamps, 1 milliamp, and 100 microamps. And depending on which one is selected, the current goes through one of these branches to this big shunt resistor that looks like a voltage divider. If you come in through the 1,000 milliamps range, it takes this path to ground and develops a voltage across this essentially 0.1 ohm resistor, precision resistor. It essentially develops 0.1 volts across this resistor when you have 1 amp input on the 1000 milliamp switch position, which is 1 amp. They just put it as 1000 milliamps on the switch. And then that 1 or that 0.1 volt just passes through all these resistors in series as a voltage and goes through another switch that's only closed in the milliamps position, and then it ignores this switch, and depending on whether it's AC or DC amps, it gets routed through the DC or AC-DC converter or the precision rectifier the same way as it did with voltage before progressing on as the input signal to the integrator. And just as with the voltage, the integrator sensitivity changes from low to high depending on which of these positions you're in. If you're in the 100 milliamp range, it goes through these 2 resistors in series, essentially 0.1 ohm in series with 0.9 ohms, so essentially a 1 ohm resistor. And notice it goes from 0.1 ohms to 0.9 ohms, but it does get that 1 ohm, so you develop 0.1 volts at 100 milliamps. So how does the meter know whether you're getting 0.1 volts because of this or 0.1 volts because of that? Well, again, it's because in those 2 ranges, 1000 milliamps and 100 milliamps, the input sensitivity of the integrator changes. So in one case it's looking for 1 volt, in another case it's looking for 0.1 volts, and that's how it tells the difference. And the same thing if you've got 10 milliamps, it goes through an even bigger resistor, so it drops the same 0.1 volts for a lesser current, and so on for the other 2 parts of the range. So it's really that simple. And if it's an AC current, then it gets routed through the precision rectifier before moving on. Okay, here's the subcircuit for the ohms or resistance measurements. There are several ways to do this, and the way this meter does it is to take a constant current and pass it through the resistor under test and then measure the voltage dropped across, and from that point on it's just the same as measuring a voltage normally. So the first thing we have to do is come up with a constant current source. And there's several ways of doing it, but this is one of the common architectures. We start out with a Zener diode, and Heathkit often liked to save a little money by putting in a cheaper bipolar transistor wired backwards to the normal polarity, thereby making it act as a Zener diode. So here we have a bipolar. The base is not connected to anything. The positive voltage is on the collector, but it's an NPN, so normally the positive would be on this side. It's reverse biased, but it behaves as a Zener diode. And then you have a resistor down here. And there is current passing through the Zener going down here, and some of it also goes through this PNP resistor or PNP transistor through this resistor to ground. This particular transistor has its base tied to its collector, which makes it act like a diode, a forward bias diode. So think of this as a diode pointing down with the cathode pointing down. And it loses a certain amount of voltage going through the transistor, but otherwise it's unaffected. And there's a potentiometer here, but we're just using it as a resistor for this part of the circuit, then another resistor, and so you have current going this way, you have current going this way, you have current going that way. It all ends up with a certain amount of current going through this. This point here, the voltage on that is also shared with the base of this other transistor. This is two transistors in one physical package, so if there's any temperature changes that might affect their characteristics, they're both going to be affected equally. Then if you put a resistor like this one from some positive voltage through this transistor, you get a constant current through here. And that's because the base is being held constant, and the base is being held constant because there's a constant voltage developed here as a result of the current through it and the constant voltage here. So that's just one of the many ways of getting a constant current source. This resistor here is tapping off of whatever voltage you get here, and notice this is only a 20K resistor and this is a 50K resistor, so the majority of voltage of the 12 volts is dropped here and here. That's 57K. So there's not a lot of voltage being dropped across this 20K resistor. So this wiper is pretty close to being 12 volts. You can move it down a little bit from 12 volts, and that changes the voltage that's at the top end of this resistor, which is what determines what the constant current is. This maintains the constant current. This determines what the constant current will be that gets maintained by this. And by wiggling this value up and down a little bit, we can fine-tune that. This is actually the 100K and 1 megohm range adjust. And it's done by adjusting the voltage, not the resistor. Now, what if we're not in the 100K or the 1 meg, which is labeled as 1000K on the front of the meter? What if we're in the 100 ohm range, for example, or the 1K range? Well, then this is again another gang of the front panel rotary switch. Then you use, from plus 12 volts, you use this resistor in series with this variable resistor, this 1K adjust trim pot, and it's used for both the 100 and the 1K range, and then it becomes the resistor that specifies the current that this transistor will regulate. And you say, well, this one isn't disconnected, but it's 5.5 megs, where these are much lower values, 1K in series with 6.5K. These overwhelm this resistor, and it's like it's not even there. It's orders of magnitude away between these resistors and these, so any effect this has is negligible on the current when one of these is engaged. Now if you get up to the 10K range, then we have this different resistor and this potentiometer in series, making an adjustable resistor, and it does the same thing. It's still so what's it about? Probably about 50K, but that's a couple orders of magnitude lower than this resistor, so once again this has no effect on it. So essentially you've got 3 adjustable resistors and series resistors, or an adjustable voltage, in this case a fixed voltage in this case, and then in this case adjustable resistors, in this case a fixed resistor, but some element between the voltage and the resistor is adjustable. It has the same effect here. If you're in the 100K or 100 ohms and 1K range, you get 1 milliamp constant current. If you're in the 10K range, you get 100 microamps constant current. And if you're in the 100K and 1000K or 1 meg range, you get 1 microamp constant current. And that just passes through this low value resistor and this diode, and it's available in any of the 5 positions of the range switch that apply to resistance. That constant current passes through here. It goes through 2 switches that are only closed when it's in the volt or ohm position. It bypasses this series resistor. These are the same, or the series capacitor. These are the same components that are used when we're measuring voltage. It's just going, the signal's going this way instead of that way through them. We're not interested in blocking DC when it's a DC signal, so the capacitor here is shorted out. We go through the same protection fuse, and we go out through the volt ohm jack, through a test lead, through the resistor that we're testing, and back and through the common to circuit ground. So we have a constant current that goes through the resistor under test and to ground. Because it's a constant current, we just apply Ohm's law to it, and the voltage developed here is the voltage across the test resistor, and hence it's proportional to the resistance. So we get a voltage comes out of here. Once again, because we're in the ohms mode, it goes through this contact of the switch. It's applied to all 5 positions of this gang of the range switch. And if we're in the 100, 1K, 10K, or 100K ranges, it comes through this contact. If we're in the 1000K or 1 meg range, it comes through this contact. It must have just been some limitation on the way the switch was built, because they're electrically tied together even though they're separate contacts on the switch. So basically the signal just passes through this switch as long as it's in one of the 5 resistance ranges. There's a little filter capacitor here, and it's passed through another gang of the same switch, also in any of the 5 resistance ranges. Then it goes through all these switches here, and it ends up going into the integrator, just as if it was a voltage being measured. In the 100 ohm range, if you put a 100 ohm resistor in the test leads, you'll develop 0.1 volts across it, and that's the voltage that's applied to the integrator. If you're in the 1K range and put a 1K resistor out there, you'll get 1 volt. Well, we already know from past experience that there's that gang of the range switch which changes the input sensitivity of the integrator on some ranges. The 100 ohm range and the 100K range are 2 of those where it shifts gears. So it's looking for 0.1 volt when it's in this range to get a full scale. It's looking for 1 volt to get full range when it's in this this part of the range. If we're in the 10K range and we put a 10K resistor, we get 1 volt. If we're in the 100K range, you put a 100K resistor, you get 0.1 volt. Again, the input sensitivity of the integrator is changed so that that works out correctly. And then finally, in the 1000K or 1 meg range, you develop 1 volt if you have a 1 meg resistor. And as I mentioned here, you get the high sensitivity mode in the 100 ohm or 100K ranges. So as I mentioned before, these voltmeter chips and even discrete circuits that don't use ICs tend to use the same basic system. It's a slope integrator type of circuit with a comparator. If you know you're ramping a voltage at a constant rate or a linear ramp here, it's an absolute straight line, and then you compare it to a voltage that you're testing, the amount of time from when it starts integrating or ramping to the time it crosses the voltage that you're testing is proportional to a numerical reading relative to the thing you're testing. So if I had a low voltage I'm trying to test, it doesn't take very much time to integrate from here to here. And if we stop counting when we get to this cross, then you'll have a smaller count. By contrast, if you're trying to measure a larger voltage or a resistance or a current which has been converted to a voltage, it's still a larger value. It takes longer to integrate from here to here, so the counting gets to be bigger during that period of time. Therefore, there's a larger number to be displayed, and because this is linear, the number you get in the counter is proportional to the value you're measuring. That's the essence of the circuit that's being used. But this is not a single slope circuit. If it was a single slope, it would be going like this. It would ramp up. At some point it would cross your test voltage, and then it would just drop back down, ramp up again, and do it like that, and count the amount of time from here to here or here to here and display that. That's a single slope integrator. There's a problem with this. What if after you calibrate it, some component value in the integration circuit changes due to heat or just age or whatever? Now you'll have an inaccurate value because it's going up at a different rate and it's crossing the measured voltage at a different time, so the count will be different during that time, therefore you'll get an inaccurate value. So the dual slope ramps down, and then at the same rate it ramps up, same rate it ramps down, same rate it ramps up. So there's a dual slope for each repeat. This is one cycle, this is another cycle, this is one cycle, this is another cycle. So during a cycle you get two slopes instead of one. The slope in this case, where it's going down, you can treat that as like the calibration. It's using all the same component values that are used to integrate up, but this time it's just being used to set an internal reference. And then when it goes back up, that reference compensates for any changes in the slope on the way up. That's an oversimplification, but that's basically what's happening. So it's like doing a controlled test where you don't care about the input voltage or the input signal, and from that, from the rate of the slope, you learn about any changes that have occurred in the circuit, and then on the way up you apply those same standards, and therefore it compensates out any drift in the circuit, and it makes a more stable, accurate meter circuit. So we know that ultimately we have to be able to ramp down and ramp up at a constant slope, and we know that we have to have some comparator function to detect when the slope crosses the voltage that we're trying to measure. So unlike the later voltmeter ICs that were monolithic in the sense that they contained all the circuitry, including display drivers and all the logic and all the analog circuitry, all wrapped into one IC, really easy to use. This one is a little earlier, and they have all the logic components in the IC, but the analog parts are not in the IC. There's a counter in here. I already mentioned that we count up during the slope of the integrated ramp and stop counting when that ramp crosses the voltage we're measuring. So that counter is in here. The clock that drives the counter is in here, and it's controlled by a capacitor to ground. Well, to calibrate this so the chip is operating in its optimal range, Heathkit chose to have 4 capacitances from 300 picofarads, 620, 1300, and 2200 picofarads with solder blob jumpers. Again, I wish they would have just used regular jumpers. They did it the kind of solder blob kludgy way. It's a little less expensive. But what you do is it's almost like a binary pattern. By blobbing over some but not all of these pads, you put different combinations of these different value capacitors in parallel with each other, and that varies the speed of the internal clock, and that's the way to get the clock close to where it should be for optimal results. The rest can be dialed out through the calibration adjustments, but you don't want to be having the calibration adjustments fight an inaccurate clock speed. So that's why that's there. here's the integrator, and it's just like I said before, it's basically just an op-amp with a capacitor tied from the output back to the input. And I should have probably diagrammed this separately. Okay, I've gone and sketched it up. So this is a simplified integrator, but even this simplified version would work in many circuits. In this version of it, we put a capacitor as the feedback element on an op-amp going from the output to the negative input, and then we reference this point to ground, usually through a resistor. If you didn't have the resistor, then it would be ground and it wouldn't work. Then you apply an input signal or some voltage to this, and it integrates because of this, a capacitor going from the output to the negative input. In that sense, it's like an inverting amplifier, but it also acts as a comparator, comparing the voltage reached on the capacitor to the input voltage and switching the output. So let's say the output goes positive. This being a comparator, the output is only high or it's low. It's like a digital signal. Let's say it's high, so now you're charging the capacitor in this direction. The voltage here is increasing, and it'll finally reach the point where it's the same as the input voltage that you're measuring. And when that happens, because this signal is rising and it's on the negative input, now the negative is higher than the positive, and it causes the output to flip to a low value. Well, when it's low, it starts discharging this capacitor, and therefore the voltage here falls. At some point it falls below the input, and it flips the other way and starts the cycle again. So that's the essence of what we've got here in the circuit with this op-amp down here. It has a stabilization capacitor. It has the capacitor from the output to the input by way of this resistor here, and then there's a ground reference hanging out here through this resistor. So if you just pretend like this point of my pencil is ground, then you've got exactly what I sketched out. And then your input signal comes in here through this resistor, and it comes from this whole switching thing I've already described in all of its permutations. So there's a couple of enhancements here. There's a little filter made with two capacitors and a resistor. And there's also two transistors wired as diodes back to back. One's facing this way, one's facing that way. This is a clamp to restrict the input voltage to this IC, prevents damage to the IC in case some crazy thing gets hooked up to the inputs. So low pass filter, it doesn't allow any high frequencies coming through. This meter would not be able to handle any high frequency signals or rapidly changing signals. It has to be pretty steady state or slowly changing. So this low pass filter only allows low frequencies to go through, and if the voltages are out of line, then these transistors clamp it to a safe value for the IC. Then you get your integration like I described it before, and then you have your output. This is just a conditioning circuit here which converts the output of the integrator slash comparator to a signal that this IC can accept as an input. So how do we control the speed of integration? Well, one thing we can do is inject a constant current into this point. By that way we can control the rate of integration. So what do we have over here? We have something very similar to what I looked at in my sketch of the Ohms mode, constant current sources. Over here I've got a bipolar transistor, reverse biased, no base connection. It's behaving as a Zener. It's feeding through one half of a two transistor package whose base is tied to its collector, and the voltage developed there is also connected to the base of the other transistor of the pair, and it has an adjustable resistance from positive 12 volts going through it, and it develops a constant current going in this direction. This circuit is turned on and off by this transistor. So it's either providing a constant current or it's providing nothing, depending on whether this transistor is on and off. And that's controlled by the output of this IC. When it wants a positive current, a positive constant current, it turns this on, turns this transistor on, allows this circuit to work, and it develops a constant current going this way. It's a positive constant current. What if this IC wants to have a negative current being generated? Well, then it comes down here and it's inverted. This is the same circuit here as we had up here, except everything is flipped upside down. These are NPN transistors, these are PNP transistors. This is a PNP transistor. Well, this one is also, but in this application it doesn't matter. These are certainly flipped upside down from here. Otherwise the circuit is a mirror image. The bottom of it's minus 12 volts, and this transistor operates as a Zener diode connected to this, and that controls this, and there's an adjustable resistance from minus 12 volts coming up to here, and this whole circuit is turned on and off by this transistor, which in turn is turned on and off by this transistor, but this is an inverting device in this application. So when this says I want to have a negative current, it inverts that so that it'll operate this guy properly to control this. And so this guy generates a negative current in the sense that it's sucking a constant current through it from whatever it's connected to. Both the positive constant current and the negative constant current circuits come together here, and that's run over here, and it's going to this point in the integrator. So when this IC here wants us to have the positive ramp, it turns on the one circuit, which provides the requisite constant current to get this to integrate in one direction. When it wants the ramp to go the other direction, it turns the other circuit on, and it pulls current out of this circuit and causes it to ramp in the other direction. So here we have a precision, stable, temperature compensated, dual constant current source that, by being controlled from this IC, causes the ramp to go up or the ramp to go down. The integration happens here, the comparator function happens here, the output is conditioned and fed back in so the IC knows where it's at and can alternate back and forth with these. Meanwhile, the clock that I already described is counting up during the appropriate ramp, and when the comparator here says, hey, the integrated ramp has reached the input signal, it flips this IC knows about it, it stops the clock, latches the value, and sends it out to the display. And then the cycle starts again, and it all happens about 5 times a second. The other thing that this IC controls besides the digits of the display is it controls the position of the decimal points, because it provides a scanned matrix display driver functionality, and therefore the decimal points must be included in that scanned matrix, so this chip has to be in charge of the decimal points. Well, you could do it off board, but it'd be a lot more complicated, and the chip is designed to control the decimal points. But you have to tell it when you want the decimal points to be turned on and off, so the correct decimal point position is activated in the matrix scan that's under control of this IC. So this looks like just a little switch here. It turns on and off, and it either there's a resistor to plus 5 volts that pulls this high, but if this transistor turns on, it pulls it to ground. So depending whether this transistor is on or off determines whether this sees a logic high or a logic low. and the input of that is fed from a circuit point called CT, and I've drawn a dashed line here so I could find it. It goes all the way up here to this point, and that goes up here, and that goes up here, and it's tied to another gang of the range switch, switch 5, and depending on which range you're in determines where the decimal point should be. And it's not enough to know that, the timing is involved also, so it's not just that a decimal point has to be turned on in a certain range, it's where in the matrix scan of the display, since in reality only one digit lights at a time, it's bing, 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 over and over and over. These signals here, 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 and here are the signals that are controlling these digits. So we know when each digit's being illuminated, that information is passed up here through this part of the range switch, and depending on which range we're in, it thereby determines when we have to turn on the decimal point so it lights in the appropriate position. That's fed back here, like I said, back down here through this transistor switch, and it turns the decimal point input on or off at the appropriate time in the matrix scan to get the correct decimal point to light up in the course of the scan. So on to the display drivers now. Being a matrix scan controller IC, that's part of its functionality. It has display segments A, B, C, D, E, F, and G, all as outputs. And if you're not familiar with it, here are the 7 segments, A, B, C, D, E, F, and then G is in the middle. That's the standard pattern for 7-segment displays. There's also the decimal point, which is another segment, but it's not a segment of the digit. So the IC turns on whichever segments are appropriate to cause the right pattern to appear on one digit at a time. And then it says, well, now I'm going to output the pattern for the next digit, and it changes the pattern here. It turns on the different digit segments, but again, only this one is lighting up. And then it does the same thing for the next and the next. This one only has positions B and C on it because all it has to form is a 1. So it's essentially acting as if it's this part of another segment. And you could do that. If this particular display had another figure 8 7-segment pattern, then you could just use the B and C segments of it instead of having a dedicated pair that's just there to display a 1. This particular display, instead of having that, it puts the plus and minus symbols there, which are separately driven, as I already mentioned. So the IC knows which pattern has to be appearing on each of the digits, and they're all in latches in here, and it goes through one after another, starting, probably with this one. Maybe it goes the other direction. Let's say it starts with the right-hand side and goes left. It'll output the pattern for that, and then tell another circuit that we're only going to power this digit. Then it'll turn that off. It'll power this digit and turn on only the segments for that digit that should be on. Then it'll turn it off, power this one, turn on the segments for that, and then finally turn on this last thing, which this all counts as one digit. So then it turns on the appropriate patterns here. That's the essence of matrix scan displays, and all of that logic and timing is done as part of this IC. I already described how the segments come out, but again, the P1, 2, 3, and 4, which are these 4 digits, are all controlled here, and they all go through 4 identical circuits and make their way up to these points here. Now there's a lot of fluby dust on here, which is misleading at first, but these are DC operated displays. They're gas discharge. They're like DC operated neon bulbs essentially, with, you can think about each segment or decimal point or plus or minus shape being one little neon bulb. And each digit has its own anode, and conventional current flow says that the current flows from the anode to the cathode. All these are cathodes. And the cathodes then come back through these drivers here and return to ground. There's also the need on these to have a negative 170 volt potential applied to them. I'm not sure why. I haven't been able to find any data on this particular display. It does need a very low current, negative 170 volt applied to it, but that is not switched on and off. It's just applied to it, and it's part of what makes it work. But as far as the active part that we're concerned about, you've just got an anode and 7 segments per digit. And as long as you put plus 170 volts, positive 170 volts on the anode, and provide a place for current to go from that through the segments and back to ground, then that segment or segments will light up. So let's look at the digit driver first. Let's say the IC wants to turn on digit 1. So it puts a signal out here, it turns on this transistor. That in turn turns on this transistor, which is fed from the positive 170 volt power supply. So that voltage is applied through this transistor up here, and here for the sake of convenience on the schematic, they just say to anode 1, and then you have to know to jump up here, and this is where that signal comes in and it goes to the anode. Ignore this junk up here. It goes from the anode, and the voltage is applied to the space between this and these segments here, and some current flows through there, and it'll light up whichever one it flows to. That requires a path to ground from each of the segments you want to light up. So those all come out of here, A through G, for this digit, and those appear on these transistors. Let's say you want to turn on segment A while this anode is energized with 170 volts. So we find A, and we go down through this transistor, and if that transistor is turned on by this IC, then it provides a place for the anode current to flow out of the display through this transistor to ground, and thereby turning on that particular display segment. And the same thing is replicated for all the other segments. As part of the appropriate biasing and operation of these transistors, they all need to have their cathode or their collectors pulled high at all times. So each one of them has a pull-up resistor going to this bus, and that is tied, actually it's not 170 volts, it's something less than 170 volts. Let's see what it is. Well, I redrew it up here to make more sense. So here's plus 170 volts. It goes through a 220k resistor and through another 220k resistor to ground. So that's a 50-50 voltage divider. Thereby 85 volts, half of 170 volts, is developed here. So I wrote 85 volts in there. And that's filtered with a capacitor. That's this capacitor down here. And then it's applied to all these pull-up resistors in the transistor circuits. That's these guys here. So they're not actually, the collectors aren't actually pulled up to 170 volts, they're pulled up to 85 volts. And then they operate based on that, but they also pull current from the displays. So I've covered how the IC here controls the ramps and the slopes and reads the output from the comparator, controls the integration on the comparator integrator circuit, and it latches the display data, and it scans the output from the latches in a matrix scan pattern to operate these. I've described how the resistors or the transistor circuits are used to drive the anodes and the cathodes on the segments. So all of that is been described. There's a few more little things going on here. The plus or minus isn't directly driven from the IC. The IC, in fact, only gets positive voltages because when we're measuring DC, normally we'd have a positive voltage here, but this meter can display negative voltages. So how does it handle that? Well, I won't go into all the details here, but this integrator can ramp up and down, and depending how the current sources are controlled, the ramp can be associated with a negative voltage or with a positive voltage, and it's all in the timing here. It's when the internal logic circuit here controls the positive and negative constant current sources. It's how it's looking at the output of the comparator and controlling the comparator by way of the constant current sources. And so it's able to keep track of, based upon how it's controlling the current sources, and when the comparator reacts to crossing the input voltage level, from that it can figure out whether it's got a negative voltage or a positive voltage. And internally it says, okay, you know, I'll deal with that. It's all built into the logic, and we don't have to worry about exactly how it does that. But having said all of that, it needs to somehow tell us that there's a positive or negative voltage. These positive and negative points here are just additional cathodes, as if they were any other segment, but they're under digit 4, and their wiring comes out here, and it's controlled by these two transistors here, and they just provide a path to ground, just like all of these transistors for the other 7 segment patterns. Same circuit. And just like these, there are pull-up resistors on all the collectors, and there are pull-up resistors on these collectors, and they also go to this plus 85 volts that's developed down here and used by all these other pull-up resistors. So these circuits are just like 2 more of these circuits. They just look funny because of the way they're drawn. These two, therefore, control the plus and minus signs, and their bases are controlled back here, and a lot depends upon what switches are in which position, and from that it can kind of figure out what's going on. And it's time sensitive because it's part of the matrix scan. So I won't get into it any more than that, but it's a fairly clever way of doing all of this. And then finally, the decimal points. I already mentioned that because the IC knows which digit is being turned on at a time by these drivers, and then that's passed up here through the range switch, and that signal is not only fed back to tell the IC here when it should turn on a decimal point to get the decimal point in the right position, that signal is also fed to yet another transistor that controls the actual decimal points, because the decimal points are being turned on indirectly from this IC by virtue of knowing that a decimal point needs to be turned on, and it knows where you are in the scan, and it's all very tricky, really. You can wrap your head around this or try to wrap your head around this for quite a while before it finally gels. But that's the essence of it. So the only thing I have left to talk about is the power supply. Okay, I'm doing the power supply last here. I've already covered how the basic battery charger works, and that essentially because the meter is powered off of this position, and this position goes through yet another gang of switch 5, which is the range switch. It's also the power switch. Whenever we're in any position besides off, the top or plus side of the battery is connected through this switch and into the power supply circuits here. If the batteries are dead, then the power that's normally used to charge the battery comes through this diode, and it does charge the battery, but it also then goes through this power switch and on out into the power supply circuits. If the battery is fully charged or nearly fully charged, then its voltage is so close to this voltage that the diode here is reverse biased and it doesn't even conduct. It's like it's not even there. So the meter is then running only off the batteries. It's only when the battery voltage drops enough that this diode is forward biased that the batteries get charged and the meter circuit's being powered off the transformer instead of the batteries then. So we already talked about how an AC reference voltage is derived from here, but now we've got this switch circuit. It's used in two ways. One is it's already talked about the battery test circuit, where it's tapped off and it's run up here through all the switches and used for measuring the batteries. The meter circuit measures its own batteries. But we need plus 5 volts for logic and some analog. We need plus and minus 12 volts for the analog for both the integrator and the precision rectifier op amps. And we need to generate the plus and minus 170 volt high voltage stuff. So let's look at the plus 5 volt first. We have this half wave rectified and unfiltered voltage coming here from the battery charge circuit, comes through here, and it's applied to a series pass transistor whose base is just tied to ground. And well, you think, well, that doesn't look like a voltage regulator circuit, does it? There's no feedback. How does that work? Well, it works for a couple reasons. First off, there are no ICs in here which are true logic ICs. The only logic in this entire thing is done by this IC, and it doesn't care exactly what its voltage is. It should be about plus 5 volts, but it's running on a battery-powered circuit, and the meter might not even be plugged into AC power, and it can work for quite a while as its battery voltage slowly drops. So this IC obviously has to be able to work on less than 5 volts. So what essentially we have here is we're just taking the half-wave rectified signal, running it through a transistor whose base is tied to ground, and it's a PNP transistor, so it's always turned on, at least some, and that output is then applied to this set of 3 capacitors, which are filters, and there's a small value resistor here as well. So it's not a regulated power supply, really. It's an approximately 5 volt source, and it's used by the positive side of the precision rectifier, and it's used as the power supply for this IC here. I think that's the only place the plus 5 volt is used. It's pretty low current. Now let's look at the higher voltages, the plus and minus 12 volts and the plus and minus 170 volts. Let's start out down here. Well, all we have here is a piddly little 5 volts or thereabouts to work with, whatever's coming off the battery or through the transformer through this diode, which is approximately the same thing, somewhere maybe close to 6 volts. It could be 5 volts or lower. There's this oscillator circuit, 2 transistors, 1 NPN, 1 PNP, and they're connected back to back in a crisscross fashion. So the collector of this one is fed back to the base of the other one, and the collector of this one is fed back to the base of this one. That builds an oscillator when you do that. And the rate of oscillation is controlled by the capacitance and the resistance that are here. Both of these have a 0.01 microfarad capacitor across a resistor, 0.01 across a resistor. So each of them has the same constant, time constant, and they flip back and forth equally. The RC values are calculated to provide a flip-flop speed, or an oscillation speed, appropriate to drive this transformer. And the middle of the transformer is connected to ground, and the center of these two transistors is driven from this approximately 5-volt signal up here through a choke, which helps isolate the rest of this circuit from the high frequency garbage going on here. So because where a capacitor will let AC through it, an inductor resists AC going through it. Since there's AC going on here from this oscillator, we don't want that to couple back into here very much. It could mess up the plus 5-volt supply. That's why this inductor is here. It also is able to store some energy, and there's a capacitor here to help provide a little extra energy to power this circuit when it's turning on and off. Because of the way these capacitors are connected in here, these transistors don't turn on hard. They kind of ease on from no conduction to full conduction, and then the other one eases on, so it provides a gradual current flow from the 5 volts through this guy to this side of the coil, or through this transistor to this side of the coil. One side or the other, the coil is energized in opposite polarities, and that sets up an AC magnetic field in this transformer. So let's look at the output. There's 2 windings on the secondary. This one has a full wave bridge, and it has 2 small value capacitors, 2.2 microfarads, 2.2 microfarads, with ground in the middle of them. And then there's this interesting circuit with 2 NPN transistors connected in this way. We have to assume that initially, since there's voltage here, that goes through this resistor and turns on this NPN transistor. Therefore, it conducts, and its current goes through here and on out. But if the current gets too high through this resistor here, then it develops a voltage across it, and that voltage developed here is placed across the base to emitter junction of this transistor, starting to turn it on. And when you turn it on, it starts stealing base current from this transistor that would normally be coming through here. It starts stealing some of that current, and therefore that turns this guy off, and it conducts less, and then there's less voltage being developed across this resistor. This transistor starts turning off, and so on, and you develop a little feedback right here. Essentially what it's looking for is to develop a certain amount of current coming out of this. In that sense, it's more like a current regulator than a voltage regulator. But what is it applied to? It's applied to this big stack of resistors here and these 2 Zener diodes. So the current, well, it's filtered again here, and then it's going through these 2 Zener diodes, which will develop a voltage across them, and then that returns to the other side of the diode bridge. So the actual voltage regulation is being done by these 2 Zener diodes, and this is more like a current controlled, or a controlled current source for these 2 Zeners. And because they're referenced to ground in the middle, half the voltage is developed from here to here, and half of it's developed from here to here. And because the middle of them is tied to ground, this voltage is considered to be minus, and this voltage is considered to be plus. So that's how we get a plus and minus voltage out of this. And each of those voltages is filtered with a capacitor to ground in each case. And because these 2 capacitors are also referenced to ground in the middle, they filter their respective half. You can look at it that way anyhow. Now we've got this big voltage divider, 110K, 110K, 17.8K, 17.8K, 2000 ohms, 2000 ohms. So they're mirror images of each other. That works out where you have plus 12 volts up here because this is a 12 volt Zener. And then because of the voltage divider here, you end up with 1.9 volts. Here, it's just used as a calibration test point. And then a test point of an unspecified voltage here. And then the same thing is available on the negative voltage divider, but here we don't need a negative 1.9, so even though it's available, there's no test point hanging off of it. So we've developed 3 test points useful for calibration and testing, and a plus and minus voltage source that's used by, for example, the op amps and a bunch of other stuff, used by all the constant current sources. And now I'll talk about the high voltage part of it. So just like this guy here, we have another winding on the transformer. It's also a full wave bridge, but its negative side is tied to ground. There's a small filter capacitor to its positive side, and then a resistor capacitor filter. It's only 2.2 microfarads, so you know there's not much current being pulled out of it, or that filter capacitor would be way too small. But with a small amount of current, it's enough to fill in the gaps between the cycles, the parts of the cycle coming out of the bridge. So you get a reasonably stable positive 170 volt voltage here. Well, you'd think, well, we'll just take the minus 170 off the other side of this bridge, but no, that side is tied to ground. There can be no minus developed from this. So the minus is actually its own little circuit, but it's still tapping off of this same winding. In this case, it works a little differently. Whenever the voltage on this winding is positive, it passes through this capacitor here and through this diode to ground. So we can charge this capacitor up when this point here is positive relative to ground. When it goes the other direction, then this diode is off and this diode is positive or forward biased. And the action of these two and this guy builds up a small voltage across this capacitor here, and that is the minus 170 volt source. With a 0.02 microfarad capacitor, you can tell that if this is to have a chance of having a steady voltage on it, it's a very low current power supply when it's done this way. But it is minus 170 volts, or pretty close to it. And like I said, the only place that's used is for something in these display modules that needs it for some reason. I just don't know what that reason is. So I think I've covered everything in this circuit. It's probably, I don't know, it's probably going to add up to well over half an hour of circuit description.